So you can hear, excuse me for that. So you can see here that we have our whiteboard up for week 2, lecture 2. Reminder that you should be reading ahead. Reminder that you have the chapter 0 spreadsheet to submit if that hasn't already been due. So remember to see Canvas as well as the dates at the beginning of live lectures if you catch them live, but only live. Practice your Excel stuff over and over and over. We will be covering 1.1. We will finally get into some section-based material today. So that MyMathLab homework will be due. Again, see the due date from the beginning of the video or what is registered in MyMathLab. And remember, assignments are generally due about a week after they have been gone over. Sometimes I might give you something slightly different, maybe a week and a couple of days if I decide to, take this a different way, but I always let students know one way or another when they're due. Your first official Excel assignment, again, chapter 0 isn't an official homework because you had to create it from scratch. The first one where it's already pre-formatted, you should now be able to download that heart rate file. Remember, it's not too much that you actually have to do in that. It's a pretty short assignment and what's expected of you. Read the instructions carefully. See MyMathLab for that date. Should be a week from today, maybe another day or two. Just pay attention to the dates at the beginning of the videos or what's listed in MyMathLab. And then you will have your first discussion board assigned as well. So we'll be talking about that during class. And once again, the due dates will have been posted before this and online in Canvas. All right. So what we're going to do is we're going to start in chapter 1 finally, and you're going to see me pull up the guided worksheet, guided activity. Remember, you can get that through the e-text. Go to chapter 1 and then it'll be on the bottom on the left side. Remember, you've got to know the ins and outs of where everything is, how to access it if you don't own the physical version of the workbook, that is. All right.
Here is the guided worksheets for chapter 1. And usually you have your definitions section. You're more than welcome to fill those out. That's not something I ever actually, again, I'm not going to be collecting these and grading them. It would be a little more like that. I wouldn't necessarily collect them, but I'd look at them more if this was a regular class, but it's not, so we got to do what we got to do. We'll go over most of these definitions, not necessarily in a full-blown, absolute, definitive definition, but more of a, hey, this is a good way to think of it. And then we have some activities. So page 28, you'll see this referenced in the guided worksheet that you have to do. So you'll be answering some of these, some more definitions, some more questions, And yeah, so that's what we'll be discussing today. And that's kind of how things will flow. And I want you to notice that, this question, this activity, look at this, buying a flat screen TV, month, balance, interest, new balance, month 1, month 2, got a whole bunch of stuff set up, and I'm going to be covering this in class some today. I've already got a template made for this. The colors aren't there, but that's okay. This is going to be good enough for us. It's all we need to worry about. And if you go in your textbook, remember I said how important your textbook is, how these things kind of cross-reference each other? All right, so this is interesting. Talks about functions. Hey, look at that. Senators and states and senators and birthdays and social security numbers. That was on that guided worksheet. So maybe you could refer to your textbook when you do that discussion, if you really had to. It doesn't have all of them, but it might give you a good start. Anytime the page is purple, I've said at one point, but this means PKA, prior knowledge assessment. So this is stuff that you should already understand for this class, but if you don't, then you definitely need to read it. And then example 2, computing a credit card balance. You buy a flat screen TV for $1,000 at Best Buy, APR 12%. Look at this. That looks just like the guided worksheet. There's even a video for this. So I'm going to say this for the 9,000th time. Your textbook really does cross-reference a lot of the stuff that we will cover, either in guided activities, what I do in a lecture. So it is important that you're putting your eyes on this. Okay, so let's go ahead and get into this. I just want to go ahead and do some blanket definitions for you. Remember, how you take your notes is up to you. I encourage most people to write. Some people don't learn by writing. If you don't learn by writing, if you just learn by reading and listening, then if it works for you, that's fine. But if you're making C's and D's and you're not writing your notes, maybe try writing your notes, you know, study skills, note-taking skills, all important things. So the idea of a function, this can get really hairy in a traditional mathematics class if we were doing, say, pre-calculus. We talk about whether functions are invertible and all this other nonsense that we're not going to get into in here, so I'm not going to allude to too much of it. But in here, in this course, everything that we handle is a function. And I'm actually going to skip down to what a function definition is because it's a little more important. Each input can only have one output. So an input is a number that goes in, and output is a number that comes out of it, as you can see here. In, out, in, out. What are these things going into? What are they coming out of? They're going into and coming out of a function. So some people like to draw up a machine diagram for this, and we have inputs, and they're in a circle, and then they go to a function, which is a rectangle for reasons, and then they spit out outputs. You literally can't confuse these in and out. In is what goes in, out is what comes out. Now, a function doesn't have to be mathematical in nature. It can be one of a trillion things. A function could be a blender. What do you do with a blender? You put an orange in. You put it into your blender. And what do you get out of it? You get orange juice. Or maybe you put an apple in. Hopefully you've decored it first so you don't break your blender. And then you get apple juice out of it. Or maybe you put a banana in. And it might not sound like the most appetizing thing in the world, but you would get banana juice. Your function doesn't have to be a blender. Your function could be an oven. I wish the eraser didn't stay like that. So your function could be an oven. So what do you put in an oven? You put in uncooked food, just in super general terms. And what do you get out of it? You get cooked food. So there are all types of functions in the world, but what we're going to be dealing with generally is Excel. Or just mathematical functions in general. So what do? We put numbers into Excel, and we let Excel do those calculations for us. I'm speaking in very general terms here. And then we actually get different numbers out of it. So I could say numbers, I could say different numbers, I could say answers. There's several different ways we could phrase this. Again, I'm just speaking in very general terms. This is nothing that you're going to be, blanket definition terms tested on kind of thing. The idea is inputs go into functions and they spit out an output. Now let's go back to the idea of the blender. When I put an orange in, I turn it on, it blends up and I get orange juice. I pour my orange juice, I wash out my blender, and then I put another orange into it, I turn it on and I get more orange juice or several oranges. And I pour, I clean, I put an orange in or several oranges in, I turn it on and I get orange juice. This is how a function should operate. When you continue to put the same input in, you should be getting the same output. That's what this parentheses statement says here. Repeated inputs can't have different outputs. Repeated inputs is me continuing to put oranges into the blender. And if I keep putting oranges in the blender, I should get the same answer, which means I can't get a different output. So every time I put my orange in, I should get orange juice. If all of a sudden let's say I go and put an orange in, I turn it on, and I get grape juice, then there's clearly a hole at the bottom of this blender leading to another dimension where oranges turn into apples or whatever I just said. So that blender would not be functioning properly. It's got like some kind of interdimensional portal thing going on, right? Or maybe it's just someone left apples in the blender and didn't clean it out. You know, it could be something simple like that. But even still, it's not functioning properly. So that is the idea of a function, but we're going to be sticking with numbers throughout this course primarily. So let's say you've got an Excel function, and this Excel function is supposed to calculate how many miles you can go in your car, depending on how much gas you have. So if you put 10 gallons in as your input, and it says that you can go 200 miles as your output, every time you put 10 gallons in, it should spit out 200 miles. If all of a sudden you put 10 gallons in and it spits out 300 miles, that thing is not functioning properly. There's something that's gone wrong somewhere. It's not a function. So again, the idea of a function is each input can only have one unique output. It's not that I can't write orange juice overall. You can have the same thing happen over and over and over. I can put an orange in, I get orange juice. Round 2, I put an orange in, I get orange juice. Round 3, I put an orange in, I get orange juice. So it's okay to get the same output over and over and over. It's just you can't get a different output from a repeated input. So a domain is just a list of all your different inputs that you're going to use for your function. A range is a list of all the different outputs. This is not something we focus on too heavily in this course, but again, just giving you blanket definitions for now. Independent variables are your chosen values. These relate to your inputs. Independent inputs, in. What goes in, what goes in. Dependent, they depend on what you put in. So these are your outputs. These are your calculated values. These are the things that if you keep putting the same input in, you should keep getting the same output. So if you keep putting the same independent variable in, you should keep getting the same dependent variable. A special definition that, again, something we won't really focus on for the rest of the course, but it's just good to introduce it with the idea of functions, in that a one-to-one function means that each input has a unique output not tied to another input. So I'm going to give you a couple quick examples of some things that are functions, some things that are not functions, and some things that are one-to-one. All right, so we're going to do this as a table of values, or just a table since these are going to be words. So this is what goes in, what comes out. You might refer to these as X and Y. It doesn't really matter. So let's say we put our orange in and we get OJ. We put our apple in and we get apple juice, AJ. And then I go and put another orange in and I get orange juice. This is a function. Because I have repeated inputs, this is kind of a red flag, or a yellow flag really. It's a yellow flag that the input's repeated, but these match. I'm only putting at the orange juices here, which means that's okay. It is a function. So this is a scenario we were just describing earlier. However, if I put an orange in, first I get orange juice. I put an apple in, then I get apple juice. Then I go and put another orange in, and all of a sudden I get grape juice. GJ for grape juice. This would not be a function because I have repeated inputs with different outputs. Those are different. The same input led to different answers. That doesn't really seem to make sense. And I think a lot of people can agree with that on a more basic level, that if you keep putting the same number into something, you should be getting the same answer. That's that classic definition of insanity. Insanity is doing the same thing over and over and expecting different results. So not being a function is kind of like insanity. Being a function is kind of like being sane. Doing the same thing over and over, putting an orange in, got the same result. This is insanity. Putting an orange in, doing the same thing led to different results. Some people also might call that chaos theory, but that's not quite right. And let's not get into that. I love chaos theory. and I'll end up talking about it for hours and just derail class completely. Let's do this a little differently now. Let's say I put an orange in, and instead of saying orange juice, I just say the output is juice. And then I put an apple in, and I just say that the output is juice. And then I put some grapes in, and I just say the output is juice. I never even repeated my inputs. So this is a very obvious one with practice, of course. You're not going to know it out of the gate. I was saying the word not, and it made me write the word not. That's my bad. That's what happens when you're reading, writing, and thinking at 3 different speeds. My apologies. We don't even have repeated inputs, so this is automatically a function. So again, this is a super easy one because none of these 3 things repeat. The only thing that says something isn't a function potentially is if you have repeated inputs, and it's if you have repeated inputs, it's the different outputs that actually makes it not a function. So again, the yellow flag is having inputs repeated. There's no yellow flag here. These are all different. But when you get that yellow flag, it's, all right, we got repeated inputs. Are the outputs different? Oh, no, they're the same function. Oh, these are different, not a function. All right. One-to-one. Each input has a unique output not tied to another input. So this says that one in can only lead to one out. One of these 3 examples is one-to-one, the other 2 are not. Now, if it's not a function, then it's not one-to-one. So this cannot be one-to-one because it's not even a function. In order to be one-to-one, it has to first be a function. So this is definitely not one-to-one. So it's the first or the third that's one-to-one. Let's see if we can figure this out. Each input has a unique output not tied to another input. So orange leads to orange juice. Orange leads to orange juice. Apple leads to apple juice. These all seem to be tied independently. Orange is always leading to orange juice. Apple is leading to apple juice. I think this is one-to-one, but let's look at the last one to see if we can confirm that. Like I said, one of these is one-to-one. Each input has a unique output not tied to another input. Orange led to juice, apple led to juice, grapes led to juice. So again, it's a function, no repeated inputs, so not even an issue there. But each input has a unique output, not tied to another input. Look at this output. It's tied to orange. So if I see that output again, it better be tied to another orange. But no, this output of juice is tied to apple. So that is not unique. It is tied to separate inputs. So it's kind of like the opposite of the function testing. Function testing is you're looking for repeated inputs. One-to-one testing, you're looking for repeated outputs leading to different inputs. So that last one is not one-to-one. The first one is one-to-one. Again, you have repeated outputs, but they're tied to the same input, so that's okay. That is one-to-one. You might see like one test question on this for the midterm, but this is not going to be something studied extensively. It's just understanding that if you put the same number into a mathematical equation or an Excel function, that the output should be the same each time if you're putting the same number in each time. So there's no insanity in this. Now, here's the thing in things like pre-calculus and calculus, insanity can exist, but we're not going to get into that. So there are still equations in math that are not functions, and they're perfectly fine. They just don't have a couple cool features that functions do. But again, that's outside of our pay grade. So with that in mind, let's take a peek over at the workbook. Where is it? Here we go. So we got some definitions, all of which you've already seen, so you could then go and fill that out if you really like keeping your notes in your workbook, or it would just be a really good idea of where to have definitions in your own notes, if I hadn't already called them out. So guided activity 1. And let me just zoom in just a touch. Here we go. The annual cost of a car is a function of many inputs. List all of the inputs you can think of that determine the output of the annual car cost. Now, man, oh man, are there a lot of inputs that could be here. So this is going to be one of your first questions for your discussion board. And you're going to see me say, I don't have
Just doing some quick video editing. Da, 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 da.
this worded perfectly for the second part, but so for discussion page 28, list 4 or more possible answers to question 1. And I'm actually going to leave this kind of as an open-ended instead of just 4 because we have so many students. Let's try and go for, 10 more. I think that's possible. If we get stuck at 8, that's okay, but I don't really see us not being able to achieve at least 8. And I don't want to spoil hardly any of these. I might spoil 1. And instead of talking about a car, let's talk about a house, because houses are similar to cars in some way. They're very different. Most cars do something called depreciate over time, which means they lose value, unless you've got a 1968 Mustang Shelby GT 500 KR with the 420, I don't know why I just said 100, with the 428 under the hood. That's a really, really special car, and it appreciates, it gains value as long as you take care of it. And as it says in Ferris Bueller's, as long as you wipe it with a diaper every day, or whatever that joke was. And that wasn't the same car. I'm just using that as a silly example. So homes tend to appreciate in value as long as you have upkeep. Cars tend to depreciate, but there's exceptions to every rule. But you have to do a lot of the same things to cars as you do homes, like one thing I just kind of mentioned, maintenance. And maintenance is a very, very generic word. There's a lot of different types of maintenance that exist. So like with maintenance of the house, you could say roof repairs, updating the kitchen appliances and carpets, and maybe building additions, mowing your yard, buying equipment. All sorts of different things go into maintenance of a home. So instead of just one student saying maintenance, if this question was about homes, you could list all those different things. And again, I wouldn't want one student just to list those things. I would want several. So maybe a student lists 1 or 2. Try and keep it at 1 because we're trying to give people opportunity here. Now, if you have an answer off the top of your brain right now, and you go into the discussion board and someone's already answered it, maybe try and come up with another one, of course, because like we said, there's a whole bunch of possibilities, and people might be fighting for 1 or 2 answers. And this isn't really the type of thing where you can say, where there's going to probably be someone saying, no, that's not going to affect a car cost. Because again, the question to 1 is the annual cost of a car is a function of many inputs. So I basically gave away one of those, lots and lots and lots and lots of others. So let's really dig into our minds trying to do that. I'm going to have these set up as threads. So whoever makes the first response, I'd like threaded responses to that, so that we don't have this question being answered, then someone comes in and answers later questions, and then someone below that's coming back to question 1. So let's try and keep these organized and threaded like you'd see on social media. So then you'll do questions 2 through 4. So what are questions 2 through 4? Determine which of the following are functions. Ooh, there's a whole bunch of these. And I already even mentioned that you kind of got some answers somewhere. Now, if you just say the answer, that's okay, but you could give some logic and reasoning to this if you would like. So determine which of the following are functions. So these are just yes or no answers. So for question 2, you'd want to come in and say states versus senators, senators versus states, and then yes. So if I think the answer to the first one is yes, then in my discussion board, I would say states to senators, yes. Or I'd say no if I think it's no. Now, there is one thing I want to mention about the senators. So we're talking about the number of senators to a state. So this is the question you need to be asking yourself. where's my text? Here we go. For number 2, you should be asking yourself, are there more than one answer in the output? Is there? I was going to change my phrasing a little, and I'm just going to go with this. Is there more than one answer in this output? So, and I said number of senators, that one's the third one. The first one is actually the senators. So I'm going to spoil this. There are 2 senators per state. I'm not much for political science. Admittedly, I'm someone that tries to keep my head buried in the sand when it comes to news because it just isn't good for mental health sometimes. I still watch some, but definitely not as much as other people. What was my point there? Okay, so states versus senators. There are 2 senators per state. So if you were to say name a state, so I'm going to say Virginia, then the output means name one of the senators. And I can't remember the name of the other one. I'm Googling it right now. They are Tim Kaine and Mark Warner. So Virginia has 2 senators, Tim Kaine and Mark Warner. I can remember Mark Warner, I just couldn't remember Tim Kaine. And opinions aside of them, if I say Virginia, then the output is supposed to be a senator's name. Whoops, didn't mean to do that. So if I say Virginia, it's a function if you can only say one senator's name. But if I say Virginia is my input, I could say a senator from Virginia is Tim Kaine, or I could say a senator from Virginia is Mark Warner. That sounds like 2 different answers. And the whole thing with functions is if you have one input, Virginia, you're only supposed to have one answer. So I've basically given this first one away, whether it's a yes or no, but I haven't said it. Now this first one is different than the third one because that compares states to the number of senators. So the number of senators for every state is 2. We're no longer trying to name them independently. The answer is just, all right, if I say Virginia, the answer should be how many senators are there? There's 2. If I say Virginia again, how many senators are there? There's 2. That's not 2 answers. That's a single answer where the answer is 2. The answer could be 5 or 7 or 5,000. It's just that there's only one answer. So again, I've basically answered whether this is a function or not. The second one swaps the first one. So if you say Virginia, and again, I said there's 2 different senators, so the answer could be Senator A or Senator B. It could be Warner, or it could be Kaine. So that implies something about whether it's a function. But what happens when you flip the script on this, when instead you say senators to states? So if you say Mark Kaine, I just combined the 2. If I say Mark Warner, the output you're supposed to say the state that he is a senator of. So if I say Mark Warner, the answer would be Virginia. Now there is a second senator of Virginia, so if I say Tim Kaine, the answer is Virginia. But Mark Warner doesn't work for 2 different states. He only works for Virginia. So Mark Warner, that's one answer. If I say Tim Kaine, that's one answer. So again, I've basically said whether that's a function or not, but I haven't said yes or no. Those are the things you're trying to do with these. Some of these might be a little more interesting, like people to number of spouses. So we're going to ignore, so a lot of times for these, we have to, I'm still on text, which is why that's happening. Let's go back to mouse. So a lot of people will say, well, there are groups of people that will marry more than one person at a time. And we're going to exclude them from this argument for the official answer. So a lot of times with these discussion boards, there will be cases where there might be 5 or 6 or 12 different answers for something. We tend to go with simple cases only. So with people to number of spouses, let's go with the simple case, the standard American fare, where you can only be married to one person at a time. So we're going to ignore a certain group of people and not to insult them or anything, or to, it has nothing to do with that. We're just keeping the case simple. So there is a definitive answer when you keep that one simple. People to anyone they've been married to, we don't have to keep that simple. I mean, spoilers, there's divorce. Divorce happens. It's a fact of life. So maybe there's something having to do with that there. Social security numbers, we're going to keep this simple. We're going to assume that no one's had their social security number stolen, whether it be your teacher at TCC, who quite literally all of us had our social security number stolen a few years ago, but we won't talk about that. Or some mob level stuff. So again, we're going to keep it simple for things like that. Shoe size, let's just pretend that every person has one shoe size. Yes, that might be different from brand to brand, but me, I might wear a 9 in one brand and a 9.5 in another. I'm just going to say my size is a 9.5 because that's usually what it is. So don't say that a person has multiple shoe sizes. We're going to just say it's one universal size per person. And a lot of these they flip the script, like I like to say, that old school lingo. So a lot of these, they'll say, all right, well, maybe it's a function one way, but not the other. If you have any of these where if you flip-flop them, it's a function both ways, guess what? That means they are one-to-one. So it'd be really cool if you get something that's one-to-one that you acknowledge that when you're doing your discussion board. And I'm not looking for paragraphs. A sentence is nice enough. If you can say it with a couple of words, that's fine. There will be times where we're looking for deeper analysis. This is not the time for that, though. Number 3, come up with a function between two quantities which remain a function when you switch the inputs and outputs. This one can be quite challenging, but I want to see if at least a couple people can get one of those right. So make sure you're referencing question 3 if you're doing that. I need to clear my screen because of that text following me. And why did I think there was a 4th one on that? Come up with annotate. Then do questions 2 through 4. I don't have a question 4, so it's just 3. My bad. So that's your first discussion board. Let's see, question. So remember, you're going to be answering these in Canvas. All discussion boards will be posted in Canvas. It says right here, Canvas. Why am I still on annotate? No. Come off of annotate, please. There we go. If for some reason I ever did one that was outside of Canvas, which I do not anticipate, I would of course let you know. And again, I know that we had a ton of questions about where and how to submit this Excel file. The only other Excel file you'll be submitting in Canvas is going to be the project. That's a long ways down the way. All Excel homeworks are just inside of my math lab purely. You will be downloading them and then uploading them to my math lab. Remember, we said that this one was the odd person out. All right, so then, what happened to my page number there? That was weird. So the next discussion board we're going to have, which I want to get into their definition stuff, is more definitions. And these definitions, some people like to call these formulas. I like to call these, pardon the pun, principles or concepts. And the pun's principle because you see that word in there a few times. Some people will call these formulas. Some people say they have to memorize these formulas. Okay, you could argue that. But you could also argue that these are very basic quantitative concepts or principles. These will be seen all semester long. Now, we may go a couple of weeks or even a month without using them at one point, and then all of a sudden they come back, and they come back in multiples. We're doing this repeatedly all of a sudden again, and then maybe it goes away for another week or two, and then we're doing it a whole bunch again. So APR stands for annual periodic rate. I thought I had that up here. So APR is annual periodic rate. Oops, can't do that. When you talk about an interest rate, whether it's for a savings account or a credit card or a home loan or layaway, we're typically referring to an annual periodic rate. In other words, this is the interest rate over 1 year. So if you had an APR of 3%, that means that you would be gaining or losing 3% of the value of whatever you're borrowing or lending out over 1 year. Now, an APR is only true if something is doing what we call compounding interest annually. And in the real world, it is extremely rare that interest is compounding annually, which means one time per year. This is something that we're going to get very heavy into throughout the semester. So an APR is the interest rate if you just pretended, because it's usually pretending, that interest only accrued once per year. But what happens is we typically feel the effects of compounding. So again, this the rate if compounded only once per year. Again, I said this is rare. So typically our accounts accrue interest daily or monthly or weekly or semi-annually or quarterly or constantly every second. So what we tend to have to refer to much more often is a periodic rate. So a periodic rate is easy to find. You just take the APR, which was the annual rate, and you divide it by the number of periods. How do you find the number of periods? You use your brain power. So if we're talking about something compounding monthly, how many months are there in a year? Well, there's 12 months in a year. I don't have that stuff up here, right? Good. Okay. This is something I usually write on the board, but this is now my board. So I will put these up here at the end. But again, let's say that you're compounding interest monthly, which means after 1 month goes by, the bank go ahead and charges you some interest. Or as 1 month goes by, if you have your money in a savings account, they go ahead and give you some interest. So what they would give you is the APR divided by the number of periods and however they're compounding. So if they say they're giving you interest every month, which means they're compounding monthly, then there's 12 months, so 12 periods. If they say that they're compounding daily, well, there's 365 days in a year. Yes, some years are 366. We're going to ignore the leap year. In fact, some people use what's known as the banker's rule, and they'll say there's only 360 days a year. What the banker's rule does is it just says there's 30 days to a month, which is not true. It's a rounded number, but it's pretty close. And it's so close, and with that very large number of periods for math reasons we'll get into much later, the difference of using 360 and 365 is extremely minimal. So it really doesn't affect the answer. It might be off by like a penny or two at worst. So how do we calculate monthly interest? So again, this is the actual money. So these rates are the percentages that you're gaining or losing every year or month or day or whatever, depending on how it's calculated. The monthly interest is the money you're gaining or losing, again, whether you're borrowing or lending. When you put money in a savings account, you're lending the bank money that they can then give to people as a mortgage payment. They can then make more money off of, and it's cyclical. So how do we find monthly interest? We take the balance of the accounts, the current balance, or the average daily balance, quite often used, but we're not going to worry about that in this course. So just the balance times the periodic rate. This right here is an extremely important concept that is just not for this, that we can find a markdown or a markup. So a markdown is a discount, a markup is extra money you pay. Or we can find a commission. We can find all sorts of things based on this simple formula, a dollar amount times its rate. If you want to find sales tax, it's the balance of what you're buying, in other words, the pre-sales tax cost times the sales tax rate. If you wanted to find a commission, you take the amount of what you sold times your commission rate. If you wanted to find a discount, you take the discount rate times what the original cost was. So this is a very generic, quote, formula just written specifically for one scenario. But it's not times the APR, it's times the periodic rate. Then we have, how do you find out the total number of payments on something? Well, it's the number of payments you make in a year times the loan term. So this is kind of a break point. These first three are really tied together. And then you'll get to this sometimes, but if you're not on a loan, then this is not relevant really. But we will do a lot of loans. If you're continually depositing money into an account like a retirement account, this will come back into play then, but we'll talk about that then. So how do you find a total number of payments? Well, it's the number of payments you make in a year times the loan term. So let's say you're paying monthly and you've got a car loan for 3 years. That would be 12 payments per year. You're paying every month times 3 years. That would be 36 payments. Let's say you're paying your house off monthly and you've got a 30-year mortgage, which is the most common. Well, there's 12 months in a year times 30 years. That would be 360 payments that you're going to make on your house. If you get a 5-year car loan, 12 times 5 would be 60, assuming you're paying your car monthly. How do you find the total that you paid for your house or your car or your boat or whatever your loan is on, your student loans? You take the number of times you paid that loan times your payment. And again, some people will call these formulas that they have to blatantly memorize, but these are very simple concepts or principles. Number of something times how long it is. Number of something times what you're paying. How do you find a total interest on a loan? So if you borrow, say, $10,000, you might end up paying $13,000 over the life of that loan because the bank's going to make money off of you. So if you paid $13,000 but you borrowed 10, that means you'd have $3,000 in interest. You just subtract those two things. But you have to find the total paid first. So it's the number of payments times the payment. So if you're paying, say, I don't know, $1,000 a month for 12 months, let's say you just pay for 1 year, that means $1,000 is your payment, 12 payments, 12 months, 12 times 1,000 would be 12,000. So maybe we borrowed 10, we paid back 12, that means the interest would be $2,000. This one right here is probably something you're not going to be that interested in. Again, sorry for the terrible puns. But it's kind of a cool number to have, the percent you pay towards a principal on something. So when you borrow money, or when someone else borrows money from you, there's interest involved. Principal is the initial amount borrowed. So in that scenario above, we borrowed $10,000, so that would be the principal. So you take what you borrowed, the $10,000, you divide it by what you end up paying for it, which was the $12,000, and then this times 100%. This really just means convert. You could just move the decimal to the, twice to the right. That's converting to a percent. Percent numbers always look bigger. They always move a decimal right twice. And the same thing in the last one. This APY. APY stands for annual percent yield. This is kind of like an effective rate due to compounding. So this has a formula. It's the total interest you get or pay over 1 year divided by the original principal and then converting it to a percent. Every single one of these, quote, formulas is one calculation. It's one computation. It's one step. You know, the last two are converting to percents, but that's because they're meant to be percents. So I don't really count that as a step in terms of a concept. How do you find a periodic rate? It's a division. How do you find a monthly interest? It's a multiplication. How do you find a total number of payments? It's a multiplication. Total paid, multiplication, total interest, subtraction. A percent paid towards principal, a division, an APY, a division. You just got to know what two things to multiply or divide or subtract. How do you know? Practice. Look at the answers. Ask if they make sense. So again, APY is an effective annual rate due to compounding. So let's say you borrow some money at a 12% APR, but you're compounding monthly, you're paying monthly, which means that interest accrues every month. You're not going to pay exactly 12% of that balance over 1 year. You're going to pay a little more. Compounding makes interest rise a little bit. And over time, it can make it rise, I'm going to say this funny, a lot a bit. a whole lot. So maybe your APR is 12%. The effective rate due to compounding might be like 12.2 or 12.3%. Or this can get even more exaggerated if you have an APR like a credit card of 24%, the APY might be like 27%. And we're going to see how these numbers compare to each other with practice and computations, but of course. So those few memos I said I was going to mention earlier has to do with the different periods. So if we compound, that means there are 12 periods because it's 12 months per year. If we compound quarterly, there are 4 quarters in a year, so there's 4 periods. Now, this might be confusing because there's 3 months to a quarter, but there's 4 periods to a year. So be careful with that one. Sometimes you're using the 4, sometimes you're using the 3. You have to practice and make sure the answers make sense, all that good stuff. If we're compounding semi-annually, that means twice per year, so there's 2 periods. If we're compounding daily, 365, or in certain cases, if you see something tell you to 360, if they say use the banker's rule. And again, what that does is it just calls every month 30 days. It's rounding it out, which is not true of January, February, March, May, July, August, or October or December. You should, in this class, know which months have 30 days, which ones have 31, and then February is the special one. There's a mnemonic device for that I can't remember, like 30 days has September, April, something like that. However it goes, Google it. If you use that, that's awesome. I was taught the Knuckle Rule, and this is really difficult to do without a camera. But if you make a fist in both of your hands, and then put your fists together so that your knuckles are kind of all aligned. Maybe I can, I'm a really bad artist, so just go with me. So here's finger, and then the divot between the finger, finger, divot between the finger, and you should have 4 of those. So there's your first fist, and then here's your second fist. Please laugh at this. I hope you're laughing. So you start at January is the first knuckle, and then February is the indention. March is the next knuckle, and April, May, June, July. August is the first knuckle of the next hand. September, October, November, December. So you get a little spare, but any month that's on a knuckle has 31 days. Any one that's on an indention doesn't have 31 days. I don't know why it works, but it works. It's just a cool fact of life. Someone taught me that when I was very young, and it's stuck like glue to me. So that's how you can remember your days of your month if you like that. If not, find another way, but that is something that you should know. It could come up at some point. All right, so again, quick review. APR is the annual rate that you would pay exactly if you only compounded once per year. Almost always, we're not doing that because the real world very rarely compounds monthly. So we typically have to go to a periodic rate from that, where we just take the APR and we slice it up. So for instance, if you were paying a 24% APR annually, but you're paying off monthly, you divide by 12, 24 divided by 12 is 2. So paying 24% over a year is effectively the same as paying 2% per month. But when you actually pay the 2% per month, it compounds, it builds and builds and builds, again, as we'll see shortly. You know, it might be a little more than 24% as an effective rate, so that's why we have this APY. How do you find how much interest you owe or get in a month? Take your balance times the periodic rate. So if you had a balance of $1,000 and you were paying 24% APR, which is 2% per month, you take 2% times your $1,000. Now, if you're doing this by hand, you'll have to convert it as a decimal. In Excel, they can handle percents. How do you find the total number of payments? Number of payments a year times the loan term. How do you find the total paid? Number of payments times the payment. Again, these become very intuitive with practice. How do you find your total interest? You take the difference of your total paid and what you borrowed or lent. Some people will try and go straight to total interest and they'll take a single payment and subtract the principal. That is wrong, wrong, wrong. It's all the payments together. So you have to make sure you're doing this so that you can then get this. All right, so back to the workbook. More definitions, lots of those things we've already covered. So again, you can refer to that. And again, this is in your textbook. A lot of details are already in your textbook. Here are some of the things I previously mentioned about compounding intervals and we typically label this as an N. So periodic rate, where we take the APR divided by the number of periods. Again, this is typically labeled as an N. You will see that over and over and over throughout this course. N is the number of periods per year. So quarterly, there's 4 of them, monthly 12, weekly. I didn't say weekly, by the way, it's 52. That should be, I hope, intuitive. And then daily 365. Again, unless you use the banker's rule. So you can see in this table, they actually do a couple of periodic rate calculations. They take an assumed APR for the problem of 12%, and they divide it by 4, which gives us 3%. They divide it by 12, which gives us 1%. They divide it by 52, which is that, and by 365, which is that. In this problem, they talk about beforehand how a credit card is a type of loan that allows you to pay what you can afford each month above a certain minimum. There is a minimum payment for all credit cards. That is a legal binding statement because you have to eventually pay off the credit card. Now, how long it takes is up to the credit card company. Most of them have a formula set up so you'd pay it off in 5 years, but there's also some that have it set up so you'd pay off in 10 years. You can add to this balance, you can subtract from this balance. This is a very interesting type of loan because the balance can change up or down due to you. Traditional loans like cars and boats and homes and student loans, you're not adding to them ever, you're just subtracting to them as you pay it down. You want to borrow more, you get a new loan. So you want to pay above the minimum with credit cards if you can. This, oh man, I will say this 10,000 times if I had the time to. Paying the minimum on a credit card is how you never have a retirement plan. If you're going to have credit card debt all your life and never pay it anything more than the minimum, you are going to pay banks hundreds of thousands of dollars potentially, depending on how much you're borrowing in credit cards. So credit cards can be absolutely evil. They have their uses. But for now, we're going with they're bad, and you need to pay them off as quick as possible. We'll discuss the pros and cons later, much later. So, and again, here's your APY formula, which will be part of this. So this is the next guided activity, page 30, that we refer to over here. Page 30, 31, problems 1 through 4, as well as problem 5, and then problems 6 through 9. And actually, this little memo, when I did this last semester, I had a very small amount of students, so I don't need that little memo anymore. So I could just say problem 5 through 9. There we go. And I haven't posted this yet. You won't see this posted until this afternoon. Remember, we are discussing these in the discussion board in Canvas. All right, so page 30 has problems 1 through 4, then page 31 has problems 5 through 9. And I'm gonna kind of, why is it not working right now? That's okay. Sometimes my my start menu or the Windows bar on the bottom just doesn't load with my mouse. I have to hit the Windows key. I don't know why. Sometimes it works, sometimes it doesn't. So we're answering these 4 questions and these 6 questions. This is going to be an issue that pops up while we're talking about it. So let's see what we got. Let us assume you buy a flat screen TV for your dorm room that costs $1,000. You make the purchase with a store credit card that has 12% APR. So that was kind of alluded to earlier. You do not have to make any monthly payments for the first year, which sounds amazing. but they will charge interest at the end of each month. So this is a pretty common, what do they call it? Good as cash loan, something like that, where you can borrow money and they're not going to make you pay any interest for a while, but after a year or 2 years or 15 months or 18 months, whatever they say, then all the interest they've been kind of calculating to the side, if you haven't paid it off, they're going to then throw the interest at you. And now your $1,000 loan might go up to, say, $1,500. Whereas if you pay down that loan over the first 12 months, those interest amounts that they calculated, they won't actually make you pay. So you would just have a year to make that $1,000 and pay it off, and then you don't pay anything extra. But if you didn't pay that down, then they would tag on the interest at the end. Now, if you're making some payments over those 12 months, but not all of them, that would reduce your interest payments, but we're not going to get into that complication. So how much do you owe at the end of the first year? So we're assuming that we never make a payment. The interest eventually does accrue and get tagged onto our account. So we will owe more than $1,000 because we don't make any payments. So what is the principal? Remember, principal is the amount that you're borrowing or lending. So principal is the amount that you're borrowing or lending. And I'm going to set up the Excel spreadsheet. So I might be giving some of these answers away, but I'm not going to say it for now. So you will see these answers given away. What is the monthly or periodic interest rate? So how do we calculate a periodic interest rate? We take the annual rate and divide it by the number of periods. Well, they said that this was a monthly credit card because they say it's monthly payments. If you're paying monthly, you're accruing interest monthly. That's a general rule of thumb. In credit cards, it always accrues monthly. Homes and car loans, they always accrue monthly. So it's just nice to know that fact. But the information is supposed to be in the problems. So what is the periodic rate? You take your APR and you divide by, you know. Monthly interest is a function of what two inputs? Monthly interest is a function of what two inputs? There is a formula on those notes to share that tells you that. So what two values are you multiplying to get monthly interest? So you can go back to that and get that, and we will basically be doing that in the Excel spreadsheet. What is the interest charge for the first month? So we'll actually see that answer in just a minute. And let's go ahead and start setting that up, actually. So we are borrowing $1,000 with an annual percent rate of 12%, but we're paying this monthly. So the number of periods in 1 year are 12. I have got a spreadsheet set up for 12 months worth of balances, interest accruals, and a new balance. So the number of periods in 1 year is 12. How do we get the periodic rate? So again, this is an answer previously, but you take the APR and you divide it by the number of periods. Now, if you do this to the side, 12% divided by 12 is 1. So some people might just type out 1%. And that's actually what I had originally, but what I want to show this as is a formula, so that way I could change the APR and the periodic rate would change with it. So we take the APR and we divide it by the number of periods. So I need to divide these two cells. So if I want Excel to do the math, we go equals, and then I'm going to take the cell G2. I can click or type it. Hey, you mean this one? Yes, I do. Divide it by, then I need the number that's in cell G5. Click it, divide it, hit enter. And if I get 1%, that would make sense, and it does. So that's good. We get a good number here. Remember, you can change the decimal or the alignments, the decimals. I have a menu hovering over it. There we go. You can make more or less zeros. It's up to you, unless it tells you what specifically to do. All right, so this cell is going to be important. So our initial balance was the principal. I'm just going to type the 1,000 because if I do equals principal, I could do that as well, but it might affect this, it might not. So again, I could type either $1,000 here and then format it to currency, like so, or I can just say it's equal to this cell. If I do it this way, this is what's known as linking. I'm not doing any pluses or minuses or timeses. This is just linking a cell. If you go somewhere else and say, hey, I want you to be the same thing as what that guy or girl is, You just go equals and then click or type the cell you want it to match. That's $1,000. So if I change this to 5,000, the balance changes to 5,000. But let's keep it at 1,000. Interest. The way we calculate interest is you take the balance times the periodic rate. So that might be an answer previously. Hint, nudge. And that was one of the formulas. Interest is a product, your monthly interest is a product of balance and periodic rate. So I need to take the balance of $1,000, which is in this cell, and I need to multiply it by the periodic rate, which is in this cell. So I need to multiply these two things. I don't want to just do the calculation in my head because there's going to be 11 more of these, and I want Excel to do all that for me. How are we on time? Okay. So we go equals to make Excel do this for us. We take the balance, which is in cell B4, times the periodic rate. Don't click the cell that says the word, click the cell with the number. Now, spoilers, this is going to be wrong ultimately, not in this cell, but in later cells. This is going to be wrong, and it's because of the fact that when we fill down formulas, remember it likes to go down, 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 down. So it's going to want to go further down from the 1%, as we'll see. But let's hit enter for now at $10. That sounds good. 1% of $1,000 is $10. If you don't believe that, you can pull out a calculator and do it yourself. $1,000 times 0.01 is 1%. $10. Perfect. It makes sense. How do we find a new balance? This is, again, a very basic principle. Pun not intended that time. Concept. You take the balance of 1,000 and you add the interest of $10. You should now owe $1,010, but we want Excel to do this, so we say equals. I can click this cell, do a plus sign, and then I can click this cell. Hey, you mean add these two things? Yes, Excel. Good job. $1,010. That makes sense. Now, that's the balance at the end of month 1. The balance at the start of month 2 should be exactly the same as the end of month 1. Whenever you're going from month to month, or day to day, or whatever, the start balance of the next one should be the end balance of the previous one. This is going to be an extremely common theme with Excel. You have got to link these two. I need this cell to be exactly what is in this cell. So I already tried that out previously and it worked. So I just go equals here. I just need to go equals. I want you to be this one because the balance is not still 1,000. It's 1,010. Let me show that again. So I need the new balance to match the old balance. So new balance month 2 matches old balance month 1. So we go equals, click or type D4. That will make it $1,010. So for some reason, let's say this balance was, let's say the principal was $5,000 over here. The interest will change, the new balance will change for month 1, and the original balance for month 2 will change. Boom, look at that. Now the interest is $50, 5 times as much because 5 times the balance. So the new balance is $50 more, and it linked and it copied perfectly. Now, you might have thought again, well, just fill this down. If you fill it down, it makes it, well, that's weird, right? What happened there? Because it thinks it's this right here because of the linking. If I didn't link, it would just say $1,000. So that looks terrible. Let's undo that. Definitely wasn't supposed to just drag that first one down. And again, this is very common. The interest calculation was a formula we typed, and we were supposed to be multiplying this blue box by this red box. Let's see if I can just fill this formula down. So remember, hover over the fill handle with that cell active, click, hold, drag down. And actually, because I had it typed, it's not going to let me do that. I did do that intentionally. Remember, I want to do a lot of mistakes throughout this, so we learn from that. So that's not working. What do I do? Oh, no, I'm messing things up. I'm clicking, and it's, oh, geez, what's happening? Error. Oh, no, heart attack. No, don't do that. Once you get out of it, hit undo, and there you go. So our cell's active, grab the fill handle, drag, drop. And then your brain is supposed to immediately go, hey, brain, that doesn't make sense, or hey, body, that doesn't make sense. Double click the cell, and the blue and the red boxes are no longer in good spots. The blue box is good. This is what we're supposed to be multiplying with, but this red box is too low. Hey, it needs to be up here. So here's what you have to do. You have to use what are known as fixed cell references. And this is going to be a bombshell. If I can get back to it. Here we go. What did that do? Here we go. Boom, boom. So we're going to call back to this several times at the beginning of this semester. Fixed cell references. So we've been using cell references that look like this so far. Just A4, B9, Q13, whatever. That's a standard reference, so when you fill a formula down, right, left, or up, Excel will change the letter or number appropriately so that they go down, right, left, or up. But sometimes, like we just saw, sometimes we don't want one of the boxes to move in a direction. Maybe we can let it move right but not down, or maybe we don't want it to move at all. So we have to fix them, and the cash symbol is how you do that. You can put a cash symbol in front of the letter, or in front of the number, or in front of both. And that will give you one of three effects. Practice with this, practice with this, practice with this. If you put the cash symbol in front of the letter, it fixes, and fixes doesn't mean it was broken and it's now fixed. It means it keeps it there, it keeps it in place. It fixes the column so that filling a formula left or right will not change the letter. So you do this when you want to fill left or right and not have a cell move. You put the cash symbol in front of the number when you want to fill up or down and not have the reference move. Let's use this for now to just kind of start out. If you put a cash symbol in front of both, it will fix both. Which means that cell will never move. The red box, blue box, whatever, will not move left, right, up, or down if you put a cash symbol in front of the letter and the number. Again, this is something that you will see throughout the semester. This is something you have to learn. This bold note I feel like really helps when filling a formula to different rows and columns. I will show you an example of this in the next 1 or 2 classes. Excuse me. Any data from a column must have the column fixed, and any data from a row must have the row fixed. So this is going to pop up in spoilers 2 to 3 homework problems. And again, we'll introduce this. For now, let's just go with this idea of putting a cash symbol in front of both of them. So where we did the Excel formula, so this one was wrong, so let me just delete it. Go back to this one. Double click to make it active. Now the blue one we did want moving down, so I'm not going to mess with that. It's the red one we don't want moving. So this is me experimenting. Let me just put a cash symbol in front of both of them and see what happens. Okay, so I hit enter. Now if I go back to that cell, drag it down, we get an answer that now makes sense. $10.10. A little more balance means a little more interest. If I double click, the blue box is where it needs to be, the red box is where it needs to be. So because we put the cash symbols in front of the letter and the number, this one is rigid, it cannot move. And if you keep filling it down, that will continue to not move. The blue box will move, but the red one won't. All right, I'm gonna hit enter, I'm gonna undo this, and now I'm gonna do it wrong. Double click. All right, well maybe I just wanna cache everything. Let's see if that works. So now I have caches in front of all numbers and letters. So the blue one, watch what happens now when I fill down. It still says $10. I could actually fill this all the way down and it's going to keep saying $10, and every single one of them is using the same boxes because I told this one not to move by putting cash symbols in front of it. The colors are coded. So no, I did want that one to move, so I'd have to undo that, but not there. So let's just have it this way. Fill it down, perfect. Now the new balance formula, we double click, remember it shows you, hey, look at me, blue, red. Do you think you want both of those moving down? I do, so we can probably just keep them normal, fill down, yep, everything's fine. So when you've got a reference kind of off to the side, it's very common that that reference needs to be fixed in one way. When you have these tables of information, say you were trying to recreate a multiplication table, that is when you'd have a column and a row reference. Again, we will actually do that specifically. Now this cell, you could again link it manually, but everything is set up perfectly. With these these very common finance spreadsheets, you end up having to do 2 full rows before you can just fill everything down. So now I can just take this one and fill it down, and it might look a little funky for a moment. Take this one and fill it down, still might look a little funky, but when I fill the last one down, all of a sudden, all the numbers look good. Our interest is growing slightly each month. So it was jumping like 10 cents a month, and then it grows 11 cents, then 12 cents, then 13 cents eventually. And that's because of compounding, as we're going to discuss in this class, as we've already started the discussion. So I did that column by column by column. Check this out though. I can highlight all three of these in that row, then grab the fill handle, and boom, everything's fine. But I could not do this until I had a second row completed. Again, this is extremely common with finance formulas. It is because you have to link the old to the new. This is why you can't just fill down the top one, because there's no linking until the second month. You're going to see this 5, 6, 7, 8 times in here probably. So at the end of the year, you can see this is a balance. So let's go back to our worksheet, and we only have like 30 seconds left. In the spreadsheet above, what formula was in C4 and D4? So those are two answers that students can do. Which formula involves an absolute cell reference? Absolute cell reference is when you're double caching. So you can go back to that and answer. Why do we need to fill in the second row before we fill the formulas down? I just said that. Linking, that's me whispering. What do you at the end of the first year? You saw that on the screen. What is the APY? If you can do that calculation, remember the formula is the total interest in 1 year divided by the principal. So what you'll do, here's what you owe at the end of the first year, but the interest would be the difference of that and what you borrowed, which was 1,000. So you calculate the interest first, then you'll take that and divide it by the original loan amount of 1,000. And what you'll find, what you should find, is that the interest for APY is just a little more than 12%. But that is time. That does conclude 1.1. As you see, the next thing we had is 1.2. So we'll call it a day there.